We study in this lesson the interference of plane waves, that is, the pattern that is established when two waves are present in the same space and that propagate in opposite direction. So, we already studied that in the presence of a change of material, there is a reflected wave and there is a transmitted wave. We concentrate on what happens in material 1, in which there are two waves that are summarized here. And particularly, we see that the incident wave is characterized by a generic amplitude A+, and the reflected wave, whose amplitude is A-, written in terms of the reflection coefficient. Therefore, A+ is A+ times gamma. As you see, the reflected wave propagates in the opposite direction as the incident wave. We want to study what happens due to the presence, simultaneous presence in space of these two waves. Let's not forget that we are dealing with phasors and therefore with sinusoidal functions of time. And these sinusoidal functions of time have an amplitude in terms of sinusoidal function of time that is the magnitude of the phasor. So when we study this interference pattern, the standing wave pattern, what we are studying is the amplitude of the field and therefore the magnitude of the phasor and therefore the amplitude of the field of the sinusoidal function of time. So let's add these two fields and let's find that as a function of z is these coordinates, the electric field and magnetic field have these expressions in which there is the coexistence of the two waves in space. So let's study the magnitude of this total phasor, the sum of the two phasors. This magnitude is, at each z coordinates, the amplitude of the sinusoidal function of time. As you see, there is this term that multiplies everything, the amplitude of A+, and this term can be considered as a multiplicative constant, which is not very interesting. It's associated to the value of the amplitude of the incident electric field. What is instead interesting is the other term, which is the magnitude of the, as you see, the progressive wave propagating along the positive z direction and the regressive wave multiplied by the coefficient gamma. Similarly, a magnetic field has a similar pattern, but with a minus here, as you see. So let's consider the problem, which is written here again, with a slightly different horizontal axis. Instead of using z, which is the coordinate moving in the right direction, we use d as the distance from the interface. So, as you see, in particularly that z equals minus d, this change of coordinates changes simply this exponential to 1 plus gamma exponential minus 2jk d instead of plus 2jk z. So we study this function in which the variable is the distance from the interface, is d. And we neglect the presence of this additive, multiplicative term A+, because it only changes the absolute amplitude of the sinusoid. Instead, we want to study the relative amplitude of these sinusoid functions of d. As you see, what we are studying is the magnitude of the field, neglecting term A+, which is the magnitude of the sum of these two complex numbers. For this purpose, and to study what happens, we plot a complex plane in which we plot a complex number as a point of this complex plane, in which on the horizontal axis is the real part, on the vertical axis is the imaginary part, in which we can plot all complex numbers related to these expressions. In particular, we plot the complex number 1 as a distance 1 from the origin that is oriented along the real axis, this orange dot. Then we have our gamma. We don't know gamma, but let's suppose that it is real negative. Its amplitude is not larger than 1, we know it, so we have plotted it with this green dot and green arrow that starts from the origin and joins gamma, the value of gamma, on the negative real axis. Then we also observe what happens as a result of moving along the d direction. As you see, gamma changes in its phase, but not in its amplitude. And therefore, gamma changes by decreasing its phase because of this minus sign, by the amount 2 times k times d. And therefore, starting from its value at d equals 0, we, by increasing d, as you see, gamma moves along this circle, constant amplitude, and acquires a phase that is minus 2kd. 2kd is the angle of this complex number, and once we substitute in place of k its expression as a function of lambda, 2kd can be written as 4 pi d over lambda, so that we observe that the important parameters is the distance from the interface in terms of wavelength. So what is the sum of these two terms? As you see, we have this complex number, and we add the two by the parallelogram rule. They add as if they were two vectors in real space, and the sum is this one. As you see, the amplitude of the sun depends, so one never changes, but this does change, it moves, so that this amplitude does change as a function of d. And the amplitude of this phasor is the amplitude of the sinusoidal oscillation in time. So if we observe a different position, different distances from the interface, the amplitude of the electric field, we observe different values because of this interference, because of this coexistence of two waves. So, starting from the interface and moving in this direction, we observe that at the interface we have some value as the amplitude of the electric field, that is this blue curve, as you see, start from here. Then we have an increase, we reach a maximum, we have a decrease, we reach a minimum. The value of the maximum in terms of the E field is 1 plus the magnitude of gamma. The value of the minimum is 1 minus the magnitude of gamma. So you see, this maximum can be as high as 2, and the minimum can be as low as 0. But depending on the value of gamma, this pattern can be different, but is always present. So that we have this periodic dependency on the distance from the interface of the amplitude of the electric field as a result of interference between two waves. We also notice that the periodicity is lambda over 2. If we start from here, we reach in which we have a minimum. After lambda over 4, we have a maximum. After another lambda over 4, and therefore lambda over 2 is the total value, we have another minimum, and so forth. Though the pattern of the electric field is exactly the dual of the pattern of magnetic field, which is this red curve, where the electric field is minimum, magnetic field is maximum, and vice versa. And here we see that the various distances from the interface. This plot is called interference plot of standing wave pattern, and it indicates the presence of two waves running in opposite directions.